lecture. Two concepts we're going to be covering today, uniform continuity, and then another criterion for continuity, the Epsilon delta criterion. Chances are, I guess you guys wouldn't have done calculus, like a college calculus course yet, but it's a definition you'll most likely see for continuous when you go to college, is the epsilon delta. So let's start with uniform continuity. Before we write out the definition, I'm going to give you intuition for what it gives us, and the definition is going to seem disconnected from the intuition for it, and we'll do a proof to connect the two. But a uniformly continuous function is a function that you can limit how much it grows in a specific interval. So if I have, for example, a sine function, this one is going to be uniformly continuous because it doesn't matter what interval you're talking about, the function never grows by more than 2, right? Sine function goes from -1 to 1. So its height never jumps by more than 2 in any specific range you choose, small or big. Make sense? Another function that's uniformly continuous is just any line. Pick an interval, the line always grows by the same amount on that interval, so you can limit how much it grows on a specific interval. Give you an example of a function that's not uniformly continuous, and that's a parabola. So if we were drawing out the right-hand side of a parabola, for the first interval of 1 unit, how much does the parabola grow?
2.
It grows 1.
Oh.
1 squared is 1.
Sorry.
Just a regular x squared parabola. By the time we get to 2, how much does it grow? From 1 to 2, how much does it grow?
It grows 3.
It grows 3, right? Because 2 squared is 4. So we went from 1 to 4. And then we go from 4 to what?
9.
9, so it grows by 5. And then we go from 9 to 16, so it grows by 7. And in the next interval of 1, it grows by 9. And then it grows by 11. And then it grows by 13, etc. Right? And so a parabola would be an example of a function that isn't uniformly continuous. Doesn't matter how small of an interval I pick, I can't bound how much the function grows in that small of an interval if I keep going to the right. So
what about the sine function? If you choose a small enough interval, then it would be continuous.
Doesn't matter how small of an interval you pick. Here's the way to think about it. For any small interval you pick, I can always find a number big enough that it won't grow by more than that number.
Oh.
So no matter what interval you pick, I pick the number 2. It will never grow by more than 2. No matter what interval you pick for a straight line, I pick the interval. It will never grow by more than the interval, because it just grows by the interval for just a perfect line like this, right? But then if you pick a really small interval, 1, even if I pick the number 10,000, there would be eventually a point far enough to the right of this parabola that it would grow by more than 10,000 in that 1 unit. Thank you.
Yeah.
Does that make sense? That's intuition for what functions are uniformly continuous. So they're continuous functions where the rate at which they grow is somehow bounded. Now I'm going to write the exact definition for what a uniformly continuous function is. It's going to seem like how are those connected, and then we'll do an example to try and get them connected. We'll prove that a parabola is uniformly continuous. So
it's not uniformly continuous?
Is not, thank you. So definition. A function f from d to, I assume, just r is said to be uniformly continuous, provided that whenever un and vn are sequences in D such that the limit of un minus vn equals 0, comma, then the limit of f of un write this out, we could say for all UN Vn in D, the limit of UN minus Vn equaling 0 implies the limit of the image, the difference of the images is equal to 0.
Is it would be if and only if, right?
No. This being true implies this is true when it's uniformly continuous.
But not the other way around?
Not the other way around.
Why?
We had a similar thing with continuity. What did it mean for a function to be continuous? A function was continuous if the sequence converging implied the image of the sequence converged. Why not the other way around? It's just a definition.
Okay. Oh yeah,
Uniformly continuous functions are continuous. Oh, so that's the first proof we're going to do. So now we're going to do a proof. Uniformly continuous functions are continuous. So 1, let f from D to R be a uniformly continuous function, and let UN and Vn be in D such that the limit of their difference is equal to 0. With me so far? We're proving that continuous functions, or uniformly continuous functions, are continuous. So I'm starting out, let f be some uniformly continuous function, and let these two be two sequences in D such that the limit of their difference is 0. Oh, wait, we don't want that. Let's just start with here, and then see what we need to do. How do we prove that function is continuous? We need to show that if we take a sequence in D that converges to a point x naught, then the image of the sequence converges to the image of x naught. That's what we need to prove. So we need to grab some arbitrary sequence in the domain D and show that if the sequence converges to x naught, then the image of the sequence converges to f of x naught. So let xn in D such that the limit of xn is equal to x naught. Okay? So we need to show that the limit of f of xn is equal to f of x naught. Now what do we know since it's uniformly continuous? We know that anytime we have two sequences such that the limit of their difference is 0, then we know that the limit of the difference of the images is 0. So how can I continue with this? I need to come up with another sequence such that the difference in the sequences is 0.
So you're going to just say that, right?
What is another sequence I can create? I want to control it so that I make this happen.
Negative x sub n?
No, we don't want it to be negative because a negative of a negative is positive.
So it'd be just x sub n.
Just xn, or even easier, let's just make a sequence out of this x naught.
Because the sequence minus...
So we're going to take x naught, x naught, x naught, x naught, x naught, over and over again. Then the difference, the limit of the difference of the sequences is just going to be 0, right?
So why do that instead of the other?
Because then look at what we're going to get over here.
Oh.
I'm trying to show that the limit, where am I trying to get? I'm trying to get that the limit of f of xn is equal to f of x naught. That's what I'm trying to get. If I can get that, I'm done. So, 3. I don't know what to call the sequence. We'll just call it the sequence x naught equal, and in case it's ambiguous, what we're saying there, x naught, comma, dot, dot, dot. Right? Make a sequence of x naughts. Then the limit of the difference of xn minus x naught is equal to the limit of xn minus the limit of x naught is equal to x naught minus x naught is equal to 0. Okay. No questions there, right? That's pretty straightforward substitution. Okay. So then, since it's uniformly continuous, then we know that the limit of f of xn minus f of x naught is equal to the limit of f of xn minus the limit of f of x naught which is equal to f of x naught minus, or f of x naught, which is equal to, which gives us that the limit of f of xn this is equal to 0, sorry, there we go. So now I'm taking this, I'm going to move this to the other side, but I know what this limit is just equal to f of x naught, which gives me f is continuous. You follow that? Anything weird? Okay. If we're good with that, let's move on to showing that a particular function is not uniformly continuous. And we'll do f of x squared. Proof f from, I assume R to R? Yeah. F from R to R by f of x equals x squared is not uniformly continuous. Okay, how are we going to show that it's not uniformly continuous? We need to find two sequences that make the antecedent true, but the conclusion false, and we're done. So 1, observe that the limit of, maybe I'll put parentheses to specify my sequences inside of here. The limit of, not xn, I need a particular sequence, n plus 1 over n minus n. So there's my two sequences, this sequence and this sequence. You with me so far? So the limit of a difference of two sequences is equal to just the limit of 1 over n is equal to 0. So here's two sequences, n plus 1 over n and n, that satisfy the antecedent. Now we need to show that the conclusion is false with these sequences. However, let me see, the limit of f of n plus 1 over n minus f of n is equal to the limit of, what is f of n plus 1 over n? Maybe we'll do it in a couple steps. That's n plus 1 over n squared, right? Minus n squared Good so far? Which, now we see that we're going to get 2, which is equal to the limit of, let's see, expanding this out, we get n squared plus 2 plus 1 over n squared minus n squared. Right?
Minus n or n squared?
N squared.
Oh.
Oh, did I say, I wrote n squared. Yeah, if I said n, that was a mistake. Right? See the expansion there? And then, that is equal to the limit of 2 plus 1 over n squared, which is equal to 2, which is not equal to 0. And we're done. So we found 2 sequences such that the difference in the limit of the sequences was 0, but the difference in the image of the limit of the sequences wasn't 0. So when you have functions that have this unbounded growth, then you're able to do little tricks like this. So I knew that squaring these would give me a constant, for example, so I could always stop it from being 0. I don't know. Hard to connect the intuition for what a uniformly continuous function is with the definition.
But it's no worse. It's no worse than continuity itself was. And once you catch on to that, this makes a lot more sense.
Okay. So any questions about that? Pretty straightforward example. All right, let's move on to whatever we do next. Next we prove that 1 over x is not uniformly continuous on the interval. We got to start from 0. Yeah, 0 to 2. Doesn't matter where we start. So our next proof, or where we end, proof f from 0 to 2 to r by f of x is equal to 1 over x is not uniformly continuous. Okay. Pick 2 sequences. So we need to find, maybe writing out the whole proof here wouldn't matter as much as just finding the sequences, and maybe you can do it from there. What are 2 sequences such that their difference converges to 0, but the image of their difference doesn't? Okay, maybe I'm expecting you to make too much of a leap. 1. So we just got to pick some. Observe that the whole challenge in these problems is coming up with these initial sequences, and then it's just showing I was right. So observe that the limit of 1 over n plus 1 minus 1 over n is equal to 0. Right?
Okay.
But what's the image of this going to be? N plus 1, and when I minus an n, I'm going to be left with a constant.
Right. Which is not equal to 0, right?
Right. So you can already see how it's going to go once you figure out what these 2 sequences are.
Yeah, so how did you figure that out?
It
makes sense now, I guess.
I just knew they both need to go to 0, and when I take their reciprocal, I need a constant left over.
Yeah, that makes sense.
And I didn't even necessarily have to have a constant left over. We could have made an n term left over. So for example, we could have done something like
3m?
We could have done something like n plus 1 squared or something crazy like that in the denominator here instead of n plus 1. And it still would have worked. So there's infinite sequences you could have used. I thought that this was the most obvious sequence. I don't know what I used when I solved it here. Oh, I used 1 over n. I used 2 n and 1 over n, which isn't a bad one either, but I don't know, I still like n plus 1, 1. So obviously that comes out to a constant, which is obviously not 0. Instead of an unbounded sequence, but okay. The next big proof of this, last big proof of the section, is proving that if we have, you'll notice over and over again, what we've been interested in is functions that are continuous on a closed bounded interval. I don't know if you've noticed that we've been working with those over and over again. Closed bounded interval and then functions on those closed bounded interval. Why did we like those closed bounded intervals? It's because sequences in them, then we have the sequential compactness theorem.
Right.
So we proved the sequential compactness theorem, which was on closed bounded intervals. So then we keep being interested in functions whose domain are closed bounded interval. And that's not going to go away. We're going to prove that. We're going to prove lots of things for them, but a lot of times when we're dealing with a derivative, we're going to be using closed bounded interval. But basically, every time we're dealing with an integral, we're going to talk about function on closed bounded interval. So there's a reason that we keep using these closed bounded intervals, and that's because we like the domain. We like sequences in the domain closed bounded intervals because the sequential compactness theorem holds up. Anyways, all right, the proof over here in case we need to reference this. I don't know why we would. Or maybe we need to reference the definition and then we'll prove it over there. Well, no, I'll just prove it right here. I'll just erase these.
So basically, the closed bounded interval is just making it easier because that allows us to choose any sequence we want and a limit.
We know that sequences behave very nice in closed bounded intervals. And so if our function's domain is a closed bounded interval, then that makes talking about continuity nice. Because remember with continuity, we're talking about taking the image of the sequence. So we need the sequence to be in the domain. So when the domain's a closed bounded interval, we can always apply the sequential compactness theorem. So it's almost a dead giveaway anytime we have proof where we're talking about a function from a closed bounded interval that we're going to use a sequential compactness theorem somewhere along the way.
I have a question.
Yep.
So you said closed bounded interval, and then you pointed at the real number symbol.
Oh, I was just pointing to where the domain would have been.
Okay.
That's why I did that.
All right.
And just subconsciously saying we like when this.
How do we, have we, I can't quite remember, have we dealt with trying to prove with a non-closed bounded interval?
Yeah, we've done lots of proofs with functions not on closed bounded intervals. We just know that when they are on, so there's some.
I mean, proving that they're continuous.
Yeah. So we proved, for example, every polynomial is continuous.
That's unbounded.
That's, yeah, the domain's completely unbounded. That's all real numbers. We proved all rational functions are continuous. So continuity was all over the place. It's just when you have proofs that include this, then you know right out the door. If I have proofs that this is my domain and I'm somehow talking about a continuous function, then I know I'm going to be using the sequential compactness theorem somewhere. Because continuity means I'm going to need a sequence in the domain, and then the domain being a closed bounded interval means sequential compactness holds. Anyway, so we have f is from AB to R. If that function is continuous, then it is uniformly continuous. So 1, let f a b to r be a continuous function. Okay, so to prove that it's uniformly continuous, I need to grab two arbitrary sequences in the domain and show that the image of those sequences, the limit of the image is 0. So 2, let u n v n in D such that the limit of un minus vn is equal to 0. Let's see, sequential compactness theorem is going to give me, they also have convergent subsequences. I'm sure I'm going to need to use that somewhere along the way. Then there exists u sub n sub k and v sub n sub k. There exist subsequences of these sequences that converge and that they converge to a point in A, B in there. Such that, I know that those two converge to the same thing. such that the limit
But their difference would still converge to
of
0.
u and k such that the limit of this sequence equal, we'll just call it u. So such that they converge, and we're just calling whatever they converge to u and v. V and k is equal to v. So I know that we have subsequences that converge to something, call them u and v.
Wait, a subsequence converges to the same thing that...
If the sequence converges. It's not necessary that a sequence in here converges. For example, I can pick the sequence A, B, A, B. So I could alternate back and forth like that. But this has a subsequence that converges. So I could pick the subsequence A, which converges to A. I could also pick the subsequence B, 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 which converges to B.
And that's what sequential compactness says, right?
So yeah, sequential compactness says that if you have a sequence in here, here's a sequence in there, it's just alternating A and B, it's guaranteed that your sequence contains a subsequence that converges to a point in there. And it could have infinite subsequences that converge to infinitely different points in there.
I see. I'm just saying, up there you have the limit of un minus vn equals 0. Does that not mean that the limit of un...
We don't know that the limit of un exists. That's our problem. So we can't split this into a difference and say therefore they have the same limit.
Alright.
So yeah, that's my holdup right now. I'm trying to figure out how I'm going to say that this and this have to be the same thing. Then it is uniformly continuous. Okay, well I do know, since it's continuous, then I know that the limit of f of u and k is equal to f of u, and I know that the limit of f of v and k is equal to f of v. So if I can just show that u and v are really the same thing, if I can show that these are the same thing, then that means that these are the same thing, which means that the limit of the difference is going to be 0. So this whole thing reduces to u and v being the same thing.
I don't understand. When you say they're equal and then the limit of the difference is going to be equal to 0, isn't that the limit of the difference of the subsequences, not the sequences that we're actually trying to prove? If u and v are the same, then...
Oh, you're right. Yes, you're right. Let me look at what I did here. Oh, I did a proof by contradiction here. Since un converges, we don't know un converges. I have a mistake here. I'm relying on the fact that un converges, which we don't know. Un converges.
But a subsequence of un converges. So why don't you create two sequences and then choose their subsequences, because you know they converge.
Right, that's what I did. So here's my two sequences.
Yeah.
So then we have two subsequences that converge. I don't know how they converge to the same thing.
What I'm saying is, why don't you make those the two sequences where you say the limit of u sub n sub k minus u v sub n sub k.
Oh, I do know. I know since the limit of un minus vn is equal to 0, then the limit of, okay, we do know this, unk minus vnk is equal to 0.
Yeah.
Because this is still just going to be a subsequence of this thing, which converges to 0. And so I know the difference converges to 0, so the subsequence is going to converge to 0. And then that will give me that u is equal to v, but then we still have the issue that you brought up, right?
Yeah, but un, we don't know what converges.
Yeah. How do I want to say that? Then there exists then the limit of u and k is equal to the limit of v and k is equal to, and we'll call it just x naught. So there's our x naught. So then I do know that the limit of the images is the same for the subsequences. The limit of the image f of u and k is equal to the limit of f of v and k, which is equal to f of x naught. So we do know that. Now we need that these two things converge.
Why do we need that?
We need that. We need this. Here's still what we're trying to get. So if I can say f of un is equal to 0 and f of en, oh, it has to converge, because if it doesn't converge, we're going to have a bounded problem. Okay, so Kate.
When you're creating your sequences, could you have just said let them be that way such that they converge, because you know that there's a convergent sequence in that interval?
No, I need to show that for any two sequences you choose, doesn't matter what they are, as long as they satisfy this condition, then our proof holds up.
Oh. Yeah.
So assume by way of contradiction that the limit of f of un minus f of vn is not equal to 0. So if this thing doesn't converge to 0, then I should be able to find from some index onwards that this is going to be greater than some epsilon from that index onwards. Does that make sense? Let me explain big picture where I'm going with this. So we're saying that the limit of this difference isn't 0. What does that mean? That means I should be able to find some really small value such that the limit of the difference here is going to, the absolute value of the difference, of the limit of the difference here is going to be greater than epsilon from some index onwards. Right?
And we're choosing a really small epsilon.
Let me see how the book does this proof. For any epsilon, if it doesn't converge to 0, let's see, if it doesn't converge, if the limit doesn't go to 0, then this doesn't converge to whatever this converges to. If these don't get arbitrarily close, then there has to be some epsilon that they are greater than or equal to from some index onwards. Is that right? We'll just look at the author's proof real quick, because I made a mistake in my notes. What are we, 4.4?
3.4.
3.4. 3.3, 3.4. Okay. A continuous function on a closed bounded interval is uniformly continuous. That's what we're proving. Yes. Okay, let U and V and be sequences in A, B such that the limit of the difference of the sequences is 0. Yes. We need to show that this is 0. Yes. We will do so by arguing by contradiction. Okay, so suppose by way of contradiction, suppose the sequences do not converge to 0, then by exercise 12, by possibly passing to a subsequence, there is an epsilon greater than 0 such that that difference is greater than epsilon for every index n by possible passing to a subsequence. I don't know what he means by that. Possible passing, let me read what exercise 12 says. Suppose the function f from E to R is not uniformly continuous, then by definition there are sequences that and B such that, but not that. Show that there is an epsilon and a strictly increasing sequence of indices such that for each index k, oh, so that's what he's relying on.
You need to prove that first.
I don't know, did I give it to you as a homework problem?
I don't think so.
Alright, let's just continue with what he has here, and let's assume that exercise 12 is true. So, then, by possibly passing a subsequence, there is some epsilon greater than 0. Then, we should probably erase all this and just start where he does. Let's start right here. Shoot, shoot, shoot. Need to fix that mistake in my proof. So let's see. 3. Assume, by way of contradiction, that the limit of f of un minus f of vn is not equal to 0. 4. Then there exist two subsequences, u sub n sub k and v sub n sub k, such that the limit of the difference of the subsequences v sub n sub k is greater than or equal to epsilon, which is greater than 0. For all k in n. Is that what he says? For every index n. Okay, so let's try to make intuitive sense out of that rather than proving exercise 12. But showing this leads to this, he's saying, is a result of exercise 12. So if we have two sequences such that the image doesn't converge to 0, then there has to be terms in the sequence where one is always greater than the other. Let's try to make intuitive sense out of one that we did before. So we were looking at n plus 1 was one of our sequences, and n. So we're saying, remember, our sequence was 1 over n plus 1. This was the image of our sequence. 1 over n was this. This was the image of our sequence. So we're saying that if the difference of these is not equal to 0, then there should be some subsequence in these such that their difference is always greater than some positive number.
Okay. I'm missing the leap, but I guess that's to be expected.
Yeah, that's not appealing to my intuition either. I don't like that. I like that for the absolute value. I don't see why it couldn't be all for some subsequence. Don't love it. We'll continue and then come back and look at that line some more. So if we can get to that line, we now use the assumption that the domain of F is closed and bounded according to the sequential compactness theorem. There's a subsequence that and a point x naught such that that converges to x naught. From this convergence and through 10, we also conclude that still making more leaps. Here's the way he has it written in the exercise. And he's saying where un and vn could possibly be subsequences, which I don't like. But we need to use other subsequences. We need to reference different subsequences of these. Let's just write exactly how he has it, and then we'll come back to this. Then, so he goes from that to then the limit of f of un minus f of vn is greater than or equal to epsilon, which is greater than 0 for all n in n. We'll come back and look at this line more, but right now I'm going to decide on that line. Let's continue. 5. So if that is true, then same argument that we had before, but then there exists, since this is a closed bounded interval, there exists subsequences u and k and v and k such that they converge since or let the limit of u and k equal x naught, which gives us that the limit of v and k is also the same thing. So same argument we had before I erase this, is equal to x naught. And we get that from this, from line 2, from the fact that the differences of their images has to be 0. So the difference of their subsequences is still going to be 0. Right? Because we could view the difference of their subsequences as a subsequence of the sequence which converges to 0. So we have two subsequences of this that both converge to the same thing, x naught in a b. Yeah, we got that.
I'm missing that jump. How do you converge to the same thing?
Because the difference has to be 0.
Oh, okay.
Right? Because this is a subsequence and this is a subsequence. Their difference is a subsequence of this. This converges to 0. So the difference of the subsequences converges to 0. This converges to x naught. Therefore, this has to converge to the same thing.
So we're still trying to argue that.
Same argument we had here before that I erased.
Right. we're still trying to figure out that U sub n is, that it converges.
We're trying to show, we're still just trying to show this part right here. That's all we're trying to show. So we know that the function's continuous at x naught. Then the limit of f of u and k is equal to the limit of f of v and k is equal to f of x naught, right?
And that's because of continuity?
Yeah, that's because it's a continuous function. Now, I don't even like that we're doing the assume by way of contradiction here. Let's see if we can kind of ignore that. I feel like we should be able to prove this directly. Oh, same exact thinking that we used for this one. Then the limit of f of u n minus, maybe we'll start it with, oh no, we only know that it's subsequence does the same thing. Oh, if the limit of f of u n minus f of e n, here's a better way to say it, is not equal to 0, then the limit of its subsequence, then the limit of f of v and k minus f of u and k, the subsequence,
isn't it the other way around?
has to not be 0. If a sequence converges, every subsequence converges to the same thing. So we know that this sequence, the difference of the sequences, that sequence converges. We're trying to show that that converges to 0. If it doesn't converge to 0, then whatever it converges to, its subsequences can't converge to 0. There we go. That's a better contradiction. So I don't like whatever thinking he was doing here. So kind of ignore that for a second. We're still basically doing an assume by way of contradiction, right? And then we should have said assume by way of contradiction that this is not 0, and then the subsequence can't be 0, but we know that the difference in that is. Okay, that's a way easier way to do it. Sorry. So, oh, we already have our assume by way of contradiction that that is not equal to 0. Ignore this line. So since line 3, then the limit of the difference of the subsequences, u and k minus f of v and k, is not equal to 0, which is our contradiction. So since the limit of this is not equal to 0, then the subsequence, whatever it converges to, has to converge to the same thing, which can't be 0. Contradiction because we know that it does converge to 0. You follow that? What is the limit of this? F of x naught. What's the limit of this? F of x naught. What's their difference? 0. But we know that can't be 0 because of this. We assume by way of contradiction that the limit of this sequence is not 0. Whatever this limit is, it's not 0. So whatever this limit is, it better not be 0. But this limit is 0, contradiction. There we go. That's a better way to do it.
And that's basic proof, right?
Huh?
That's basically the same proof, basically.
Yeah, that's a proof. I guess we could do 9, therefore it does equal 0. And be done. Therefore, the limit of f of un minus f of en, limit of that difference is equal to 0. That was a little bit of a mess. Sorry. I don't like what the author was trying to do with this. Too much explaining. And I'm still not even sure how it's true. I have to think about it more. Because my intuition says I should also be able to make this. I don't know why. Well, no, maybe it is true. I just don't have a good intuition for it. Maybe we should just try proving that directly. But we'll call it there for 3.4. So that's the end of uniform continuity. Once again, the intuition for uniform continuity is, can I limit how much the function grows on a specific interval? For every interval you choose, can I always pick some limit such that the function won't grow, some bound, such that the function won't grow by more than that bound on that interval? On the length of that interval, whatever the length of that interval is. Okay, so now we're going to be moving on to another definition for continuity. We call it the epsilon delta criterion. The way that this definition works, this is the one that helps see the intuition for a function is continuous if when you draw it you don't pick up your pencil. And what we're saying is that it's continuous if the pre-image of open intervals is an open interval. Well, kind of. Let's write it out exactly, and then I'll draw the picture and we'll make it make sense. Definition. Function f from D to R is not a definition. This is something we're going to prove. Because we already have our definition for continuity. We could have used this as a definition for a continuous and proved our definition also implies a continuous function, or we can use our definition for continuous and prove that it also gives us this. So they're logically equivalent definitions. You can use whichever one you want. Anyways, a function f from D to R is continuous provided that. Are they going to set these up as if and only if, or are they going to set this up as just an implication?
The book says it's a definition.
Definition, the epsilon delta criterion at a point. Oh, they're going to define the criterion and then show it gives us a continuous function. Okay, that's how they're going to do it. I still don't like calling it definition now. Definition, the function f is said to satisfy the epsilon delta criterion, provided that. Alright, we'll say that. A function f from D to R is said to satisfy the epsilon delta criterion provided that for all epsilon greater than 0, comma, there exists a delta greater than 0 such that x minus said to satisfy the epsilon delta criterion at x naught, at a point x naught, provided that for all epsilon there exists a delta such that x minus x naught less than delta implies f of x minus f of x naught is less than epsilon. I'm going to write it right here. For all epsilon, there exists a delta such that x minus x naught less than delta implies f of x minus f of x naught, absolute value less than epsilon. Let's draw the picture for this now and try and get intuition for what's saying. So draw a picture. Better marker. It's kind of dying on me. Put markers around, try to get over here. Okay, so we've got some continuous function. What does it look like? Who cares? Just goes on its merry way. We're saying it's continuous at a point. Pick a random point in here. Okay, I pick this point. Here's my x naught. So the function is continuous at x naught. Here is f of x naught. A function is continuous at x naught if for every epsilon, for every open interval we choose around here. So here's my f of x naught. Now pick an open interval centered there. Doesn't matter how big, just pick one. So we're going to pick the open interval up to and down to, this is f of x naught plus epsilon, and this is f of x naught minus epsilon. So we chose some open interval around f of x naught. If for every open interval you pick, where does this map to on our function? It maps here. If for every open interval you pick around the image point, you can find an interval around the domain point. So we'll pick this interval. And this right-hand side is x naught plus delta. And this left-hand side is x naught minus delta. Notice they map to the points here and here. So they don't necessarily line up. Okay, so here's what it says. If for every interval you pick around the image, you can find an interval around the domain such that this entire interval maps inside this entire interval. If that's the case, it's continuous at that point. Does that make sense?
Yes.
Let's get over reading it this way really quick. For every epsilon, or for every, remember, epsilon is giving your interval around your image point. For every epsilon, or every interval around your image point, there exists a delta, or an interval around your domain point, such that a point being within delta of x naught, or being in this interval, implies f of x is within epsilon of f of x naught, or in other words, being in this interval. So if that's the case, then a function is continuous. So let's help establish our intuition by looking at one that's not continuous, just with a picture, and seeing how it doesn't satisfy this. You with me? So maybe we'll leave both pictures for a second. So let's draw another one. Why do I go back to blue? For some reason I was doing the same thing. So draw some function that we know isn't continuous. So a function isn't continuous if it has a jump in it, basically, right? So we've got a function, and it comes, and it stops here, and then it picks up here, and continues on its merry way, right? There's an example of a function that's not continuous. Now, where is it not continuous? Obviously, at this point. So it's not continuous at this point, x naught. What is f of x naught? That's right here. Here's f of x naught. Notice, if I pick the interval from here to here, where does that map? That maps right there. If I choose epsilon to be that distance, then here's that interval, here's this interval, right here. No matter what delta you pick, you cannot find a delta such that it maps all the points around here into this interval. Because when you come even a teeny bit to the right of x naught, you can try and make it really, really small all you want. It's going to map to points. It's mapping some of these points to points here, which is outside of this interval. Do you see it? So that's the picture as to why this definition gives you, basically, if you can draw it with a smooth line, it's continuous. Because once you have these jumps, then we're going to make some, I can map some of the points down here outside the jump, or outside this interval. So all these points are not mapped to somewhere in this interval because they hit over here. Notice over here, the image of all these points, which was right here on the line, is always inside this interval. The image of these points is right here and right here. Some are outside the interval, some are inside the interval, so this one's not continuous. Make sense?
Yes, I have a question though.
Go ahead.
So on your first graph, let's say that f of x naught doesn't exist, like that's just a hole in the graph. Does it not satisfy this criterion because f of x naught exists? I'm just like wondering how you would show that that's not continuous using that definition.
If x naught doesn't map to anything, x naught isn't in the domain. You have to have a function. So you're probably thinking about, when I was doing calculus, sometimes I gave us functions with holes in it. The thing is, in your calculus class, they didn't specifically specify what the domain was, and they expected you to imply what the domain was based off of where the function is not defined. So if a function has a hole, and it doesn't just jump, but it actually is just missing a point, like that, then the function is not defined at that point. And so that point's not in the domain, so we don't talk about it being continuous there. We can talk about it being continuous to the right of it and to the left of it, but we can't talk about continuity at that point because that's not in the function. Does that make sense?
Yeah.
And you'll notice, okay, so I try and get a point really, really close to that. Doesn't matter how close you get, I can always find an open interval that doesn't quite get past that point. Okay, so that's the epsilon delta criterion. Let's see, define f of x equal to x cubed. We claim that that satisfies the epsilon delta criterion. Why aren't we showing that this gives a continuous function first? Oh well. We'll do an example using this criterion. I'll tell you ahead of time, this is the same thing as giving us a continuous function, but we won't prove that yet. First, the author's going to do some examples, so let's do some examples of functions that we know satisfy this criterion. So, proof f from, I assume, R to R. Yeah. F from R to R by f of x equals x cubed is continuous, and we're going to do this proof using the epsilon delta criterion. So I need to show that for any epsilon you choose, I can find a delta such that this being true implies this is true. And this is very similar to proving a sequence converges type proofs. You start out with an epsilon, and now you need to find the delta. So 1. Let epsilon be any number greater than 0. And now I need to show, I need to find the delta that when this is true, this is true. And sometimes we come to the side and we do scratch work to think about how this proof's going to go. So I need, when x minus, oh, we need to prove it's continuous at a point. What point does he choose? At 2. It's continuous at x not equal to 2. So proof is continuous at 2. So I need to show that if x minus 2 is less than delta, that leads to x minus 8, x cubed, minus 8 being less than epsilon. So I need to find the delta that makes this true. See if we don't have another marker. And I can pick this delta to be whatever I want. I just need to make this true. So we basically need to manipulate this to get this side out of it, because we know that we can make this as small as we want, and I need to use the fact that I'm making this as small as I want to make this less than epsilon. So let's see. We know that x cubed minus 8 is going to equal, factor out an x minus 2. So that's going to be x minus 2 times, put a dot there. What do we get when we factor out x minus 2? We're going to get x squared plus 2x plus 2, or plus 4x plus 4. Am I doing that right? 2x plus 4. X and x gives us x squared.
Yeah, that's right.
X squared minus 2x minus 8. Oops.
Unless it's minus
X
4.
cubed plus 2x squared plus 4x minus 2x squared minus 4x minus 8. Yeah, that's right. Okay. So I know that I need this to be less than epsilon. I know I can make this as small as I want. I just need to make it so small that it also pulls this thing down and keeps it all less than epsilon. So let's see what I would want to do. Let's see the biggest that this thing could be. So if x minus 2, well, if I arbitrarily decide I'm not going to let delta be bigger than 1, whatever small number I'm going to choose, I'm not going to let it be bigger than 1, then this is kind of weird to get comfortable with the first time. How can I specify it? How can I help you see this? If we do delta is equal to the minimum of 1 and then some other small number that we're still looking for. So I want a delta that makes this true. If I say, okay, no matter what, I'm never going to let delta be bigger than 1. So if a number bigger than 1 happens to make this true, then 1 will make this true, right? I can make this delta as small as I want. I don't need to find the biggest delta that makes this true. I just need to find a delta that makes this true. You with me so far?
Okay.
So if 1 makes this true, either delta can be 1 or delta can be something smaller than 1. So if 1 makes this true, fine. Or something smaller than 1 makes this true, then we're still good. I basically just need to come up with a restriction on what's the biggest value I can get out of here. What's the biggest my x can be. So maybe I'm explaining too much before actually writing to help you see it. So if we know that delta is going to be the minimum of 1 in something, then this at most is going to be 1. So I know x minus 2 is going to be less than 1, which is going to give me that 1 is less than x is less than 3. So whatever my delta is, the biggest that this right here is going to be is what we get when we plug in 3 for x. It's never going to be bigger than that. So this is going to be, if I already know, let delta equal the minimum of 1 and something to be stated later. Maybe we'll just keep filling in the proof and you'll see it. Then we know that x minus 2 is going to be less than 1, which gives me that 1 is less than x is less than 3. 4. So then x cubed minus 8 is equal to x minus 2 times x squared plus 2x minus 4, which is then going to be less than or equal to, what's the biggest value that we can get here? If we know that the biggest x can be is 3, and this is a proper inequality, because x can't ever be 3. But the biggest number that we can get here is 9 plus 6 minus 4, right? So this is going to be less than
11.
Let's see.
Times x minus 2.
We could even be careful. Maybe we don't want to think about, well, what values really make this the smallest with that minus sign in there? So maybe we even want to say this is going to be less than or equal to x minus 2 times x squared plus 2x plus 4. Oh, that should have been a plus anyways, huh? I made a mistake. Okay, so back to how we were thinking about. The biggest that this can be for sure, if x has to be less than 3, then there's no way that this can be bigger than 19, right? So this is less than or equal to this times 19. And now we're trying to force this to be less than epsilon, and we need the delta that makes that true. So if I say delta then is a minimum of 1, and let's see, epsilon over 19, then this is less than delta times 19, which we know is going to be less than or equal to epsilon. So ultimately, I was trying to show if x minus, oh, I forgot to say that. So here's my real 3. Assume or let x minus 2 be less than delta. That was my real number 3. And then this is 4 and this is 5. And we're done. So let epsilon be greater than 0. Let delta equal the minimum of 1 and something to be determined later in my proof. I'm going to come back and fill this in. I don't know what this is going to be yet. Assume x minus 2 is less than delta. Well, if x minus 2 is less than delta, then x minus 2 is definitely less than 1, right? Because delta cannot be bigger than 1. Delta is a minimum of 1 and something. So it definitely can't be bigger than 1. So this, if this is less than delta, this has to be less than 1. This less than 1 means that x is bounded above by 3. And below by 1, right?
Can't
No.
delta be equal to 1?
Yeah, but I know that this is less than delta. So this is less than 1.
Oh, okay, yeah, I see.
Yeah, my delta can be 1, but this inequality is still a strict inequality. So x minus 2, the absolute value of x minus 2 has to be less than 1, which is the same thing as x has to be between 1 and 3. Okay. So this can be rewritten this way. The biggest that can be, since x is between 1 and 3, is 19. So this, whatever it is less than or equal to this thing, and in fact it's a proper less than sign, right? Because we can't ever actually get 19 here, because x can't ever actually be 3. So this is definitely less than this, x minus 2 times 19. Now, by definition, or by assumption, x minus 2 is less than delta. And so delta times 19, I need that to be less than epsilon. This is where you come back in and say, okay, what was the delta I needed to get that true? And that's, in general, how these proofs work. So you start out with some function f of x that you're trying to show is less than epsilon. You need to somehow get that this is less than your delta, less than your x minus x naught times a constant, which will then be less than your delta times a constant. And then to make that less than epsilon, you just choose delta to be epsilon over your constant. That's kind of how these flow. I don't know. Maybe we should just do another one. Do another one?
Yeah.
All right. Give me a function and give me a point. What function you want? You're too slow.
Okay.
Prove f of x equal to that is continuous at what point?
3.
3. All right. So that's what we'll do. So let epsilon be greater than 0. 2. Let delta equal the minimum of 1 and something to be filled in later. Assume now we're going to do assume the antecedent, show that implies a conclusion. Assume x minus x naught, 3, is less than delta. Well, that gives us that x minus 3 is less than 1. That gives us 1 is less than x is less than 4. With me so far?
I don't know if this is a good question. I'm missing as why we can assume that x minus 3 is less than delta.
We're proving this implication. How do you prove an implication? You assume the antecedent and show that implies a conclusion.
Right.
We're showing this implies this. We're not proving this is true.
But in every continuous function, is that true? No, that doesn't make sense.
A function is continuous if this implication is true. How do you show the implication is true? You show that the antecedent implies a conclusion. So assume the antecedent, and now we're going to show that implies a conclusion. So for then the absolute value of f of x minus f of 3 is equal to, what's f of x? X squared plus 2 minus, what's f of 3? 9 plus 2 is 11, so minus 11. Let's keep it this way for a second. Minus 3 squared minus 2. See exactly how we're plugging it into the function. You with me so far? Which is equal to, cancel out these two constants, and we'll just look at the cubes for a second. Which is equal to x squared minus 3 squared. Right? And now I'm going to factor this. I always want to factor because I always want to try and get this term to come out, whatever I'm making less than delta. Because I know that this is a term I can make as small as I want. So I always need to try and get this to show up. Now I know how to make that show up because this is the same thing as x minus 3, oops, not nice epsilon. That's the same thing as x minus 3 times x plus 3, right? So we were able to factor it. Okay, now I know that this is less than delta. And what's the biggest that this can be?
7.
7. So this is less than, we know this one's less than delta, and this one's less than 7. So now if I come back and I say, what's delta? Delta's going to be the minimum of epsilon over 7 and 1. Then this is going to be less than or equal to epsilon. And we're done. They're a lot like proving that a sequence converges in my mind. Similar type of thinking. But the big trick is starting out with this and trying to get this to show up again. That's what we're always trying to do. And make sure that whatever the remainder is somehow bounded. So this is going to give us our bounded for the remainder stuff. And then this is going to be making this as small as we want. In this case, we want to make it epsilon over 7. Good?
When you, just checking here, when you have your absolute value of x minus 3 is less than 1, goes to 1 is less than x is less than 4. You are, wouldn't it be, it'd be a 3 on the left hand side and you take that down to a 1, right?
So this could be rewritten as negative 1 is less than x minus 3. Oh, it's less than 2.
It was still technically true.
It's
Which
still
is still
true.
true.
Like, I figured.
Negative 1 less than that, less than 1, which then gives us 2 is less than x is less than 4.
Yeah.
Yeah, I messed up on the left hand side. Which makes sense. This should only span 2, so this should only span 2.
I do have one question.
Go ahead.
How did you say that x minus 3 times x plus 3 is less than delta?
How did I say that this and this is less than delta?
Yeah.
I didn't. I broke it into two pieces. I said this is less than delta, and this is less than 7.
Okay.
Because we know our x is between 2 and 4. So what's the biggest that this can be? 7. If x is between 2 and 4.
It can't.
Oh, I see why you're saying 6. It gets really, really close to, but never quite 7. So this can't ever quite be 7, right?
Okay.
So this is always less than 7, and then we already assumed that x minus 3 is less than delta.
Right.
So we're doing 2 substitutions there. And then, since we know that delta is the minimum of these two, then delta how can I say that without being confusing? If delta is the minimum of these two things, so it definitely can't be bigger than that. When you plug that in for delta, you get epsilon. It's the minimum of these two things. So it definitely isn't bigger than this. It could be this, it could be smaller than this. Since delta is the minimum of these two things, it can't be any bigger than whatever this is. So when you plug that in for delta, well, is that the right way to say it? Yeah, delta is the minimum of these two things. So when I plug that in, I could have only made it bigger. I might have kept it the same, or I made it bigger. I could have made it smaller by plugging this in for delta. Because delta is the smallest of these two things. Am I saying that right? Is it clicking?
I kind of get it. I don't know if I'm all the way there.
Whatever delta is, it can't be bigger than this number. Correct?
Yeah.
So if I plug that number in for delta, I could have only made it bigger.
Unless
I couldn't have made it smaller.
Are you guaranteed that number is less than 1?
No, I have no clue what that number is. That number could be bigger than 1, that number could be less than 1. I know what delta is though. It's the minimum of these. So this is the biggest delta could be.
No, it could be 1 if it's smaller than 1.
Let me say it another way.
Oh, duh, yeah.
Okay.
Okay.
Delta is either this or smaller. The only way it's 1 is if 1 happens to be smaller than this.
Right. So it's not big.
So it's this or smaller. So plugging this in for delta, we either kept it the same or we made it bigger. Is that clicking?
Yeah.
It's pretty, yeah. It's kind of like working with absolute values at first. Okay.
I almost feel like I've forgotten the point. If that makes sense.
We were proving
Yeah, I mean, I
this implication. If x is within delta of x naught, then f of x is within epsilon of x naught. For any epsilon you choose, I can always find a delta such that x being in with delta of x naught implies f of x is within epsilon of f of x naught. Or in other words, for any interval you pick around this point, I can always find an interval around this point such that the image of the interval around this point is entirely within the interval around this point. That's another way to say it. Okay, so we'll do a quick break while I set up the main proof of this section, which I'm guessing is going to be proving that the epsilon delta criterion does give continuity. So you can go on break while I set up the next proof. Let's go over the proof. That's the heart of this section. So we're proving now that the epsilon delta criterion for continuity is the exact same thing as our definition of continuous. So we're going to show that they're the same thing. So let f be a function from D to R. Then f is continuous at some point x naught if and only if it satisfies the epsilon delta criterion at x naught. That's what we're going to prove. So we're going to go the first way. We're going to go this way first. We're going to let f be some continuous function at some point x naught, and we're going to show that implies that the epsilon delta criterion is satisfied at that point. At that point x naught. For this direction, we're going to do assume by way of contradiction, or we're going to do by way of contradiction. So assume by way of contradiction that we don't satisfy the epsilon delta criterion at this point. And for those of you you guys might remember back when you did discrete math, we learned how to negate quantifiers. So remember, how do we take the negation of this thing? Remember, when you negate, you switch for all quantifiers into there exist quantifiers in for all, and then you do the not of the statement. So you might remember that if I had for all x, there exists y, some statement about x and y. If I want to negate this, then that's there exists x such that for all y, some statement, the not of some statement about x and y. Let's look at it in a really simple example to help it appeal to your intuition. What's the negation of all swans are white? There exists a swan that's not white. So there's an example. With just one quantifier, but two quantifiers is the same idea. So when we're doing by way of contradiction for this thing, we need to write the negation of that thing. We're going to assume by way of contradiction the negation of this thing. What's the negation of this thing? The negation of this thing is there exists an epsilon such that for all delta, x minus x naught is less than delta, but, or and, however you want to think about it, f of x minus f of x naught is greater than or equal to epsilon. So the opposite of for every epsilon, there exists a delta such that x being within delta of x naught implies f of x is within epsilon of x naught, means that there does exist some epsilon such that for any delta you try to choose, this is true, but this is still false, or this is still false. We're finding a case. We found an epsilon such that for any delta you choose, this is true, but this is false. Therefore, the whole implication is false. Remember, there's only one way to disprove an implication. Show that the antecedent is true and the conclusion is false. That's how you show an implication is false. So this is the negation of this. So when we're doing assume by way of contradiction, we need to understand how to negate that. So let's look at this again. Assume by way of contradiction that f doesn't satisfy the epsilon delta criterion. That means that there must exist some epsilon, call it epsilon naught, such that for any delta you choose, this inequality is true, but this is now this inequality, or in other words, this inequality is false. Good? There must be some epsilon such that no matter what delta you choose, this statement is false. When is this statement false? When this is true, but this is false. Which is what we're saying right here.
Why do you change your implication to an and?
When is an implication false? When the antecedent is true and the conclusion is false.
Right.
I'm just nodding an implication.
Okay.
If I want not A implies B, that's logically equivalent to not, or A and not B.
Right.
Those two are the exact same thing. So I could have written it this way, but this is going to be a more useful way to think about it. So then there must exist some epsilon such that no matter what delta you choose, this is true, but what we had on the right is false at that particular epsilon. With me so far? Then, for any natural number you choose, there must exist some point xn. We're using the natural number to pick a delta. So for any delta 1 over n you choose, this is going to be true. There's going to be some point in here where the image of that point, I want to keep saying it in terms of not. So since this is false, then we have this statement. So with our epsilon, for any delta we choose, we're going to choose 1 over 1, then 1 over 2, then 1 over 3, then 1 over 4. For any delta we choose, this is going to be true, but this is going to be false. So I'm going to choose a bunch of deltas here. Remember, it's true for any delta. I'm going to choose, my first delta is going to be 1 over 1. There has to be some point x within 1 of x naught, such that the image of that point is not within epsilon of f of x naught. Does it make sense what I'm saying? For every delta I choose, there has to be a point that makes this true. Right? So I'm going to choose delta to be 1 over 1. So when I choose delta to be 1, there has to be a point x in here. There has to be a point x that satisfies this and satisfies this. When I choose delta to be 1 half, there has to be a point that satisfies this and satisfies this. When I choose delta to be 1/3, there's going to have to be a point that's in here and that satisfies this. I'm going to do that over and over again to create a sequence of points. So for every n, there must exist an xn such that xn is within 1 over n of x naught, but it's not within f of xn is not within epsilon of f of x naught. Am I overstressing this, or are you still confused, or not getting a lot of feedback? Are we good with line 4, or should I keep trying to say it different ways?
I don't quite understand it.
Okay. Maybe a picture will help with this. So we're saying the not of this. So we're saying that there must exist some, so here's our point f of x naught, whatever it is, who knows. And here's our point x naught. If we're doing the negation of this statement, then there must be some interval around here I can choose, epsilon. So this is f of x naught plus epsilon naught, and this is f of x naught minus epsilon naught. If this is not true, then there must be some interval I can find around here, such that no matter what interval you choose around here, I'm going to choose the interval. So one of my intervals is going to be x naught plus, I'm going to choose 1 over n. I'm going to keep changing my interval over and over again. But no matter what interval I choose around here, if I pick a point in that interval, I'm going to get a point outside of this interval. F of xn is not going to be in this interval. It's going to be outside of it. So here's xn. F of xn is going to be somewhere up here or down there.
Because that's what
What did it mean to be continuous? For it to be continuous, it meant for any epsilon you choose, there exists a delta such that all the points within delta of x naught map to points within epsilon of f of x naught. That's what it meant to be continuous. We're doing the negation of that. If it's not continuous at a point, then that means that there must be some epsilon I can stick around f of x naught, such that no matter what interval you choose around x naught, it is going to map points outside of this interval. Not all of its points, but at least one point. That's what meant to not be continuous. Right? When we looked at our more concrete example with a jump, so when our function had a jump, how did we know that the function wasn't continuous? So our function was coming along, went right there, then it had a jump, and we continued on our way, right? So we knew that this function wasn't continuous at this point, call it x naught. How did we know? Well, here's f of x naught. We said there is some epsilon you can choose. There it is. Such that for any delta you pick around here, pick any delta you want. Doesn't matter what delta you pick. I'm always guaranteed that delta will map a point that lands outside this interval. So if I make this interval small enough so I don't jump that gap, no matter how big or small I make my delta around this point, it's always going to map some points outside this interval. Because it's going to map some points down here. And all the points down here are outside this interval. Right? This interval can only account for points here. So no matter what interval I choose around here, it's going to map at least one of my points outside the interval. That's what we're saying here. We're saying that there must be some epsilon such that for any interval you choose around the domain, when you pick a point in that domain, it's going to map it somewhere outside the interval around the image. And you can do that for any delta you want. So I may choose my delta, I may increment, but I'm going to go all the way to 1, then just 1/2 away, then 1/3 away, 1/4 away, 1/5. Doesn't matter. Doesn't matter how small I make that interval, it's always going to have a point that maps over here outside of the epsilon interval. So that's what we're saying here. We're saying for any natural number you choose, there always must be a point that is within our interval in the domain, but is not within our interval in the image. Feel like you got line 4 now?
Yeah.
It's just hard to wrap your head around this definition at first, but once it clicks, it clicks. Okay, awesome. Then, notice that how we're defining our points xn, what do they converge to?
What do they converge to? Or
I created a sequence xn that converges to x0.
So their difference
Yeah.
converges to 0.
I said, look, around delta, let's go from 1/1 and 1/1 in either direction. So this over here, this is x0 plus 1/n, and over here is x0 minus 1/n. When n is 1, then that gives me an interval, and that interval has a point, call it x1, such that the image of that point is outside of this interval. It's over here. Now switch n to 2. I can still find a point, call it x2, such that the image of that point, could be the same point, could be a different point, maps outside that interval. And I can do that for 3 and 4. Pick any n you want here, and I can always find a point that satisfies that. Call that point x sub whatever our n is. So when n is 1, call it x of 1. When n is 2, call it x of 2. So x of n is always within 1/n of x0. So xn is converging to x0. Right? Proving this converges to this if it satisfies this inequality. That's like the most trivial proof ever. How do I know that xn converges to x0? How do we prove that? We need to show that for any epsilon you choose, I can find an index n such that this is less than epsilon from that index onwards, and you get for free from the Archimedean property.
Yeah.
Right?
Right.
So that's just... So this obviously gives us that this is true. Do we see that? Okay. But since the function is continuous, if this is true, this is true. From continuity. Right? Remember, what are we trying to prove? We're trying to prove that continuity implies the epsilon delta criterion holds. So we said, assume we have a continuous function, and assume it doesn't satisfy the epsilon delta criterion. It doesn't satisfy the epsilon delta criterion is what this line was. So then we create a sequence of points, always not satisfying that epsilon delta criterion. They're within 1/n of our domain, but they're always outside on the image. We created a sequence that converges to x0, so the limit of the image of the sequence has to converge to f of x0. But what does this mean? If a limit of this is equal to this, that's the same thing as the limit of their difference is equal to 0. Right?
Can you say that one more time?
Okay. Maybe I'll just put an arrow here rather than making you have to think about. That's the same thing as the limit of f of x and minus, just say it this way. The limit of this is the same thing as this converges to this. Okay. So, oh, why did I do is equal to 0? I meant less than epsilon. Okay. So, since this converges to this, then for any epsilon you pick, there must exist an index big N such that this inequality is true from that index onwards. So here I'm saying from some index onwards, this is less than epsilon naught, but we assume by way of contradiction that it's always greater than epsilon naught. There's our contradiction. You see it? Kind of a mouthful there. Just need to look out for a bit. Okay. Let me know when you're ready to continue, or if you have questions.
I think I got it. That makes pretty good sense.
Oh, we may continue with this. Sorry. Okay, so we're ready to do the other direction now. All right, the other direction. Now we're going to assume that our function satisfies the epsilon delta criterion at a point x naught. We need to show that it's continuous. How do we show it's continuous? We let xn be any sequence in the domain such that the limit of xn is equal to x naught. We now need to show that the limit of the image is equal to the image of the limit. And we're done. Right? So let epsilon be some number greater than 0. What are we trying to show? We're trying to show that there is some big N such that this inequality is true from that big N onwards. That is what it means for this to converge to this. We're just using the definition of a limit directly on this one. We're going to directly find the N. Am I losing you?
Yeah, I'm missing how it, for some reason.
Okay.
No, I don't know what you're saying. I have lost, for whatever reason, how this is connecting to continuity.
We're now going to prove that if f satisfies the epsilon delta at x naught,
Right.
then it's continuous.
Right.
So we're trying to prove it's continuous. How do you prove it's continuous? Let xn be some sequence in there such that xn, the limit of xn is x naught.
Right.
What are we trying to show? We're trying to show that
The limit of f of xn is equal to f of x naught.
perfect. The limit of f of xn is equal to f of x naught.
Right.
That's identical to saying that this sequence converges to this.
Right.
So
Okay.
let epsilon be greater than 0. It remains to show that this inequality is true from some index onwards.
Right.
So we need to find the big N that makes this inequality true. Once we found that, we're done. The epsilon delta criterion gives us, so here's an epsilon. Remember what we have. For any epsilon, there exists a delta such that this being true implies this is true. So once you give us an epsilon, I'm guaranteed there's a delta. So the epsilon delta criterion gives us that there exists some delta such that this being true implies this is true. Right?
By definition.
Yeah, that's exactly what the epsilon delta criterion gives us. We know our function satisfies the epsilon delta criterion, so we know that this is true for our function. Now, since the limit of xn is equal to x naught, what does that mean? That means xn converges to x naught. What does that mean? That means that there exists some big N such that if xn is... Oh, that means for any epsilon you choose, in this case we have a delta there, for any positive number you choose here, there exists some index n such that this index is true from some index onwards. Right? If xn converges to x naught, we know the limit of xn is x naught. What does that mean? That means for any positive number you choose, there exists some natural number n such that this inequality is true from that index onwards. That's exactly what convergence is, right? So, this is true from n onwards. Then, this is true from n onwards. Epsilon delta criterion says if this is true, this is true. Right? That's the epsilon delta criterion. This being true implies this is true. Well, we know that this is true from some index onwards. Therefore, this is true from some index onwards. But this being true from some index onwards is exactly what we mean by it converges. So they're the same. Follow that proof? Okay. The last theorem that we cover in this section, we don't need to write it out because it's so obvious. It's just saying, show that a function being uniformly continuous means that it satisfies the epsilon delta criterion as well. And obviously, if it's uniformly continuous, then it's continuous, then it satisfies the epsilon delta criterion. So that one, I don't even think the author writes it out. I don't know, you want to see another example? We have one more example that we skipped over, or we could try and cover homework problems real quick. Questions?
I don't think I'd be able to go over my homework problems in that time. So I'll just do an example and go over homework next time.
Oh, it's just another uniform continuous example. I think the one we did was better. So, you can read it if you want. It's really small and easy to follow. It's just picking an arbitrary function and picking a point to do it at. Same as what we already did. You guys just bring them in. So that's the new material for this week. Next week we'll be covering...
The next sections? Or
yeah, images and inverse. Yeah, so even though it turns out we have a week longer on this semester than I thought, I don't like that it's at the end of the break. I don't know why they didn't just shift the break over one and give us an extra week before the break.
That is...
We have 1 week after the break before the semester ends.
I thought that was
Actually,
just...
I think
thought that
that's
was like a
Christmas.
student deadline or something. I didn't realize that was the end of the semester. That's weird.
Yeah, 1 week after that is Christmas. Like if we shifted it 1 week, we would be in school on Christmas.
He's saying that the first week of our class is in January.
I was just thinking about Tuesdays. Who cares about Wednesday and Thursday?
It's Christmas Eve, I do.
I don't know, everyone else in the school, all the other teachers.
Yeah.
That's
So it's kind of an awkward break. So we're just going to continue with how we have it planned. We'll still just, next week I'll give you everything. You can take it home.
Are we going to
You have the break to do it.
review in class?
No.
Okay.
That's nice.
See, here's the only other way that we could do it. The only other way that we could do it is
Do it over break?
no, not do it over break, is have you show up and when you first come back from the holidays, take the final.
Yeah, I wouldn't like that either.
That's the only other way to do it. Because I have to cover new material next week. Next week is our last class, so I can't cover new material and review. See, if we had the extra week, then I could review and still make it take home, and you just give it back right at the end of the holidays before the next semester starts.
But we had Veterans Day.
But we don't have that. So, it'll be take home. I'll still be doing my topology class on Monday nights. You're always welcome to come there with any questions. I'm usually there an hour early, so you can show up just around 6-ish and ask me any questions that you have.
So we're taking home 2 tests as well as doing 2 sections.
Yep, you got it. And you got a month to do it.
That's not long enough.
Wait, we're taking home the chapter 3 test, the midterm,
And there's going to be identical questions on the chapter 3 test and the midterm. So you're going to answer the same questions twice. We'll make all those open book. You just can't work together and you can't Google answers. So
oh, it's